So recently we've been talking about the quantum harmonic oscillator, which is used to model several systems, and essentially it just has a Hamiltonian that is the kinetic energy plus the potential energy of a harmonic oscillator. And we can model several systems like this. We rewrote that Hamiltonian then in terms of our raising and lowering operators, or equivalently just the number operator, where we've defined that number operator just to be the raising times the lowering operator. The raising operator defined as m omega over 2 h bar, position operator minus the momentum operator over m omega, and the lowering operator, just the conjugate of that, where this is plus the momentum operator over that. And these essentially just raise and lower the system through the ladder of energy states. We use this and what we call the operator method to determine the entire spectrum, which is just h bar omega times n plus 1/2, where n is just this a quantum number indicating which energy level we're in. And last video, we went through using the operator method to derive our energy eigenfunctions, the wave functions of those energy states. And that turned out to be equal to this. Where we had written the wave functions in terms of what we call the Hermite polynomials, and we defined this dimensionless parameter, this dimensionless variable, as that m omega over h bar, all square rooted, times x. So this sort of really quickly summarizes sort of the things we've got to so far. And again, we looked at these wave functions last video, and how they looked inside that well. What we're going to do today is we're going to build on this and use the harmonic oscillator to sort of recap a lot of what was covered in 323, the different representations, both Dirac, momentum, matrix notations. We're going to look at time dependence, the momentum representation, and uncertainty, and hopefully by the end of this, have a nice little toolkit of how to deal with and how to work with harmonic oscillator systems. So let's start with Dirac notation. With Dirac notation, we essentially indicate the state of our system with a ket, right? For this case, we've solved for the energy eigenstates. We indicate those just by using the quantum number n. Again, you might see the label En using the eigenvalue or even the full eigenvalue written out. But the gist is we have some ket with some unique indicator telling which eigenstate it's referring to when we're looking at our eigenkets that we solved for previously. These eigenstates, these eigenkets, form an orthonormal set, right? The energy is a Hermitian operator, so its eigensets span the Hilbert space and form an orthonormal set. So if we look at the inner product of any two eigenkets, an eigenket and eigenbra with themselves, we get the Dirac delta function. So 0 if they're not the same state, and 1 if they're different. We also can write any general state of our system. So it doesn't have to be an eigenstate, just be any state, as a superposition of these states. And if you recall, how we do that is we use the closure relationship. The state is equal to the identity operator times the state, but closure tells us that that identity operator is just equal to the sum of all the projection operators onto all of our basis states. And in this case, we're looking at the energy eigenbasis, so we're projecting onto those. So I can write my state vector as the projection onto all my basis vectors. And this means that it's equal to the projection of that state vector onto my basis vector times that basis ket. Essentially, or written another way, this is just a linear combination. So we have some coefficient, a linear combination of all my basis vectors, right? Where we've defined where Cn is equal to the projection of that state vector onto that basis axis, right? We can think of this same system in terms of position space. We've already described how, or sorted out last class, how those state vectors can be represented in a position representation using the energy eigenfunctions, those wave functions. The orthonormality, or sorry, the normality relationship essentially means if I integrate over all space, my energy, my eigenfunctions, or essentially my probability density, uh, this is equal to 1, right? The particle is somewhere in space. And, or, likewise, if this is, well, let's just switch it to here. If these are different states, then this is no longer 1. It's a delta function, Dirac delta function, where if, sorry, that's mn. If these wave functions are the same, this is equal to 1 and they're normalized. If they're different, this is 0. They're orthogonal. Finally, the probability of measuring some energy state, say, we just use the postulate 4, where we project onto that measured state whatever the system is in and take the square of that. And that gives us the probability of a measurement of energy resulting in that energy. So we should be very comfortable with all this stuff after last semester's class. We can use the harmonic oscillator sort of the same way we've used all our other systems and think about it in this representation. However, we can also, knowing how all our operators act on our energy eigenstates, we can write all of these operators in terms of matrix representations. In matrix representations, you have to sort of choose a basis we're going to have our matrix representation in. In this case, the only one we have so far really is our energy eigenbases. And knowing that any operator in its own eigenbases is diagonal, we immediately know that our Hamiltonian in that eigenbases is just a diagonal matrix with the eigenvalues along the diagonal. So 1/2 h bar omega, 3/2 h bar omega, 5/2 h bar omega along the diagonal, and 0 for all the other elements. And, so forth and so forth, right? Our eigenvectors in their own bases are just unit vectors. So they're going to look like this. And the eigenbras are just the column vectors, like that. So this should be pretty standard, in their own eigenbases, matrices are diagonal and the eigenvectors are unit vectors. And knowing how other operators act on these basis vectors allow us to write those operators in terms of their in matrix representations, right? So if we think of how the lowering operator acts on some vector, some eigenvector n, we know that that ends up being root n times the n minus 1 eigenvector, right? So if I want to know what my lowering operator is in matrix notation, right? Well, it's got A00, A01, A02 elements, and then A10, A11, etc., and so forth. That's what my matrix is. I know those matrix elements, A, I, J, are just that operator sort of sandwiched between the ith and jth eigenbra. So to do this, we can just figure out each of these elements by considering how that operator acts on those bras and kets, right? So for the A, N, M matrix element, we'll say we have the nth bra, the lowering operator acting on the mth state is going to give us n root m minus 1, right? Which is equal to square root m times the delta, the n m minus 1 delta function. So basically we take the mth column and the m minus 1 row and put the square root of m in there. So in the matrix representation, the 0, 0 state, well, that's 0. The 0, 1 element, rather, is root 1. This is a little small. I'm going to blow this up for us. We have, so we end up with this operator being 0, root 1, 0, 0, etc., 0, 0, root 2, 0, and so on and so forth, right? It has off-diagonal elements. And through our whole infinite dimensional space, similarly, we do the same thing for the raising operator, and we end up with 0, root 1, 0, and we keep going this way. Again, it has these just off-diagonal elements and going on throughout the whole space. One thing you can notice is in both of these cases, right, we have, off-diagonal elements here that are essentially connecting the n and the n plus 1 states for the lowering operator, and in this case, we have the n and the n minus 1 states are connected by these off-diagonal elements. They another thing is these are not Hermitian, right? They are not complex transposes of each other. So the raising and lowering operators are not observables, right? Because all physical observables are represented by Hermitian operators. So we know that. So we know a few things about that. We have them in their matrix representation. We can look at using these. We can look at our definitions of what these were. Of what these operators were, and to figure out our position and momentum operators are in matrix representation. So let's do that, right? We know that our lowering operator is equal to m omega over 2 h bar square rooted the position operator plus I, the momentum operator, over m omega. And the raising operator is the complex conjugate of that. So what we can see from that is we just take them sort of and add them together or subtract them, we're going to get the position and momentum operators. So knowing that, that gives us our x hat can be written as h bar over 2 m omega times the raising plus the lowering operator, and the momentum operator is very similar, just the raising operator subtracted the lowering operator. And we know what A and A dagger are in this matrix representation up here. So we essentially we can really quickly get the position operator in our matrix representation and our momentum operator. And it's essentially just h bar over 2 m omega square rooted, and we have zeros along the diagonal, but root 1, we have these off diagonal elements, root 2, 0, and that's what our position operator looks like in matrix representation. And our momentum operator is similarly 0. It has this negative I root 2, root 1, 0, 0, I root 1, 0. Geez, getting sloppy and rushing here. Sorry about that. Erase this. This is negative I root 2. You write that neater. It's negative I root 1 there. 0 I root 2. Negative I root 3, 0. And hopefully you can go through this and see. I'll probably give it as a homework. Show that this is the case in a little more detail. Note that these are Hermitian operators now. They are complex transposes of themselves. So they are physical observables like we would expect for position and momentum. They're not diagonal, which means they are not, this basis we're using for this matrix representation is not their eigenbases, so they do not commute with the energy eigenstates, so they are not, so we're not in their eigenbases, so we can't essentially measure these and the energy at the same time. Right. So we've got all these representations, and we can use, the position, the matrix, or the Dirac representations to make calculations. So if we wanted to calculate, let's say, the expectation value for position of the 0th energy state, in Dirac notation, we know that's just operating on that, and we can put in our what we know our h bar over m omega square root a dagger plus a operating on that bra. This lowering operator acting on that gets 0. This raising operator acting on that ket brings it to the n equals 1 ket, which is orthogonal to that. So pretty quickly, we know that's equal to 0. We also could use our matrix representation, right? That is just the 0th element of that matrix or of that operator in matrix representation, which we just saw a second ago is 0. So we know that's 0. And we could also have done this in the position representation where we essentially just integrate over our wave functions and the position space representation of that matrix operator, or written another way, x times that probability density squared. And we can see that this is 0 because, that probability density is an even function, x is odd. So if we integrate over all space, so we end up with an odd function, and integrating over all space gives us 0. So again, we should be familiar with using these different representations and how to make calculations. But we have one more sort of representation to look at, and that's the momentum space representation. If you remember, our eigenstates can be written in momentum space, where essentially we have a wave function, but rather than being sort of a probability amplitude in position space, it's in momentum space, right? The probability density that would result from that momentum space wave function squared is essentially the probability that that state is found at a given momentum rather than a given position. So how do we find these momentum space wave functions? Well, we can use a lot of the same techniques that we use to find position space wave function. We can use the operator method, because we know that the lowering operator acting on the n equals 0 state is equal to 0. And we can write that in terms of our momentum space, which ends up giving us m omega over 2 h bar square root x hat plus I p operator m omega operating on our momentum space wave function of our zeroth order. The trick is with this, we would have to realize what the x and the p operators are in momentum space, not position space, but momentum space. And it turns out they look somewhat familiar and analogous to what we are. The momentum operator is just the variable momentum, and the x operators goes as the derivative with respect to momentum. If we plug those in here, we get a differential equation because this ends up being equal to 0. And it turns out that zeroth, that would give us our n equals 0 momentum space wave function would be equal to 1 over pi m omega h bar all to the 1/4 and e to the negative p squared over 2m omega h bar, which is a Gaussian function. We could then continue and just take the raising operator and do the same thing we did in the position space representation, where we figured out the ground state wave function. We apply the raising operator to that and keep going. And what we end up getting is that the momentum space wave functions end up being equal to 1 over pi m omega h bar to the 1/4, 1 over 2 to the n factorial. We get more of those Hermite polynomials, h to the n times, this time the variable is omega over h bar, square root that, and then e to the negative p squared over 2m omega h bar. So we get a similar, sort of to what we got in the position space, except for in momentum space. So momentum is now our variable here. And we've got our momentum space wave function. We could have arrived at the same thing just by taking our Hamiltonian and our energy eigenvalue equation and looking at that in momentum space rather. We'd have to again use these operators and what they are in momentum space. But that energy eigenvalue equation, essentially, if we solve that differential equation, we would get the exact same thing. Lastly, the thing we could have done is use the Fourier transform, right? We know that the position space, the momentum space wave function is the Fourier transform of the position space wave function. So if we were to take that, integrate from infinity to infinity of our position space wave function, e to the negative I px over h bar dx, we would have gotten the, we get our, momentum space wave function. So if we take so this is just how we can get it for any general wave function, but if we were to look at this for, say, the, sorry, I got sloppy with my notation there. In general, if we want some momentum space wave function, take the Fourier transform of the position space wave function. If we wanted to look at a specific, eigenstate wave function, we would have to look at then the position space wave function of that state. If we look at the n equals 0 state, well, this is a Gaussian. The Fourier transform of a Gaussian is another Gaussian, and we get back the same thing we had here. So we have all of those tools that we used last semester in that to go from position to momentum space. But what we can do here is we can quickly look at, now that we have a momentum space and position space wave functions, especially for the ground state, we can easily look at sort of the Heisenberg uncertainty principle, right? We know that Heisenberg uncertainty gives us this, right? We have the uncertainty in position and momentum. has to be greater than or equal to h bar over 2, where these sort of uncertainties are the standard deviations of position and momentum. And then delta p would be the same thing with just p. Right? The nice thing about this is we can look at the n equals 0 state that are both Gaussians, and knowing the form of Gaussians determine what those uncertainties are just by inspection. We know that a Gaussian probability distribution looks something like this, where we have as a function of x, 1 over root 2 pi sigma e to the negative variable minus the mean squared times 2 standard deviation squared, right? So if we look at the probability distributions of from our position and momentum space, we have our position space wave function squared ends up being m omega over 2 h bar square rooted e to the negative m omega x squared over h bar. And for our momentum space wave function of our ground state, this one ends up being 1 over pi m omega h bar square rooted e to the negative p squared over m omega h bar. You can just sort of, look by inspection and see that our standard deviation in our position is h bar over 2 m omega square root, which that is our delta x. And for our momentum space, we end up with m omega h bar over 2 square rooted. That's our delta p, right? And hopefully you can sort of see this, right? If this coefficient out front is supposed to be equal to 1 over 2 pi times the standard deviation, set them equal to each other, solve for that. Likewise, you can do the similar thing over here. And that allows us to calculate the uncertainty, the Heisenberg uncertainty relation, right? What is delta x times delta p for the ground state of our harmonic oscillator? Well, it's just h bar over 2 m omega square root times square root m omega h bar over 2, which is equal to h bar over 2, right? So V, not only does it obey the Heisenberg uncertainty principle, but it is actually the minimum uncertainty state, is the ground state of our harmonic oscillator. Not only that, it is an energy eigenstate. So if we have our system in the ground state of our harmonic oscillator, it will remain in that state indefinitely. It's a time independent state, right? If you recall, our time dependence is determined by the Hamiltonian operator, and those eigenstates are the stationary states. I think that's the nice little sort of broad view of all the harmonic oscillator stuff we've done. I'm going to stop this video here for today. Next video, we're going to continue on, we alluded to time dependence there. The next video, I'll go through an example. We'll look at time dependence in a harmonic oscillator and go through our standard time evolution for systems with time independent Hamiltonians, work through a little example using the harmonic oscillator. If you have any questions, bring them up in the synchronous sessions or email me and I will answer them as quickly as I can. I'll see you then.